and welcome everybody to the first in this series of Kronos Technology webinars, looking at some of the technological challenges in smart grids. Today, I want to talk about some of the challenges in enabling the smart grids, the energy grids of tomorrow. So before we look forward, we have to look back. What do we have at the moment? Rather rudely, I've called it the dumb grid here. So before the smart grid, over the past 100 years, the electricity generation, distribution and consumption system has evolved from initially lots of independent little energy grids. In the sort of 1960s, I think, was the first time that the whole national grid came together. And traditionally, it has looked at managing itself by one of the properties of the way that the power is generated being these huge spinning machines, these huge generators, usually steam generators. Usually power generation was simply creating heat, heating water, creating steam, driving steam turbines that then drove electricity generators. So traditionally, the grid was managed, certainly in Europe, where the grid frequency is 50 hertz, by looking at the frequency that was generated. If the grid was under excessive stress and under excessive load, that frequency would dip, so the frequency would fall below 50 hertz. If there wasn't enough load, then those generators were able to speed up slightly. So typically, the management has been done by maintaining the frequency of the whole grid to within 1% of that 50 hertz figure. Now, it's done pretty coarsely, really, in terms of having large power generating assets that were able to be switched in or out of the grid if there was an extra demand, or by shedding load, by looking at the load in the system, trying to estimate and measure what the load in the system is, and then disconnecting large proportions of that load if the grid looked like it would be excessively overloaded. So to protect the grid, it's always had this self-protection facility built in, where if it looked like something serious was going to go wrong, then load could be disconnected. An example of that happened recently in the UK on the 9th of August 2019. There were a couple of lightning strikes that affected the grid at the same time, and coincidentally, two of the large-ish generating assets in the grid had technical problems at the same time. So there was a significant drop in generation capability. In 2019, at the moment, I think, and now we're in this sort of halfway house where we don't have a fully smart grid, but we do have some smart features. So some smaller distributed generation assets disconnected from the grid because they saw this, because there was a dip in the grid frequency, because a couple of generators went offline. So lots of smaller distributed generation capability dropped off the grid, and then that tripped the grid into this load shedding protection where some big industrial users and some rail users were disconnected, and in the end some smaller residential users were disconnected as well. But that affected over 1 million consumers, and there was a side effect of that was some of the rail assets that were stranded. They had particular issues with some of their safety systems, where the trains were not in the station. The safety systems wouldn't reset without engineers and technicians being tasked to the trains and effectively rebooting and restarting the trains. So the grid typically was this sort of passive one-way distribution of power from the center where the power was generated to the outside, to the edge of the grid. So the smart grid, looking forward, the smart grid compares with the generation that we've had in the past. It's more active rather than being a passive thing, and from a few relatively large generation assets, these huge spinning machines with lots of inertia. So part of the problem in managing the grid is managing the inertia of those spinning machines, to lots of different generating capabilities and new technologies as well. So not just electromechanical spinning generators, but also different generation technologies. So diversification in the sources of energy, also in the storage as well. So the old grid had pump storage systems where hydroelectric systems could pump water from a lower to a higher elevation, and then in times of need could then switch on hydroelectric generation. But now we're looking at battery storage as well as other types of converting electricity into some quantity, maybe a gas or a liquid that can be stored and then turned back into electricity as it's needed. One of the big changes is the unidirectional nature of the old grid, where the power was generated in the core in a few specific places and then passed out to the edges of the network. Whereas now we're looking at localized, this idea of microgeneration, where we have lots of small opportunities to generate electricity and pass that back into the grid. The smart grid is going to be more dynamic, more reactive on a much smaller scale. So lots and lots of assets switching in and switching out of the grid, either consuming or supplying electricity. And even this being under the control of autonomous agents. So there's this concept of a grid cell, a smart cell in the grid, where it will decide for itself, looking at the wholesale electricity market, whether it makes sense to be a consumer and to maybe store energy, or to be a supplier and offer energy back to the grid. And obviously one of the big changes we're seeing is the decarbonisation of the transport system at the moment, specifically around electric vehicles. So whether they are consumer or whether they are public transport, but the idea that now we've got this energy store of hundreds of kilowatt hours of electricity that can be stored in electric vehicle batteries, that could also be an energy store to offer energy back to the grid in times of need, to balance that that equation between the supply and demand of electricity. So if we look at the smart grid in a little bit more detail, and in terms specifically of this particular webinar, where do we need synchronization? Where does time play a part in the management of this grid? Well, as before in the existing grid, before we added these smart features, we've always had phase management, synchro phasers, that very accurately measure the phase of the generated electricity signal. So the sinusoidal 50 hertz alternating current waveform that's used across the grid, whether that's so that generators can be synchronized together so they're in phase, whether it's within a substation, so the digital substation, this IEC 61850 standard is looking at using Ethernet inside, using Ethernet process and a station bus inside digital substations to communicate between all sorts of protection and measurement elements within a substation. And indeed, synchronization and time synchronization is also useful and used and necessary in lots of microgeneration systems. Like the classic example is the solar PV, so the photovoltaic cells that that consumers have installed on the top of their house that generate a DC current that needs to be then converted into an AC current before it's fed back into the grid. And these inverters need to be synchronized to the grid. They don't want to connect their highest positive part of their waveform when the grid is at the lowest negative, because that would obviously make a big bang and things go very wrong. So grid tie inverters, synchroinverters, which are solid state DC to AC inverters, but they mimic some of the inertia that the existing system, the old power generation system, has. So there are ways, again, this sort of halfway house we're in before we get to what we could call a fully smart grid, or we still have some of the pre-smart grid issues to deal with in the network. And also the smart broker, the smart cell, the grid cell, this broker or agent that looks at wholesale electricity prices and then works out whether to buy or sell. Obviously, it needs time synchronization to be able to do that. And certainly for legal requirements in terms of buying and selling things, there's often legal requirement on timestamping transactions and getting a legally verifiable source of time that is able to then enable that surface. And one of the significant things is we're moving from this focus on these rotating machines with inertia to more solid state electronic DC AC conversion that needs time synchronization. So if we have microgeneration systems, we need a common time base for them to be able to coordinate generation between them. Distribution systems as well, if the grid is already there, if the grid voltage is already there, then it can be used as a timing reference. And this is one of the things that people notice with solar PV systems at home, a so-called grid tie inverter that converts the DC current from the solar photovoltaic cells into an alternating current. When there's a power outage, people with solar cells, if the sun's shining, think they should still have electricity, but lots of these grid tie inverter systems fail safe. They won't start, they won't actually generate any AC electricity if the grid voltage isn't there. So there's a synchronization requirement, a safety requirement for them to generate voltage in phase with the grid that's already there. And the smart grid as a whole, it's really this complex communication network that's laid over the top of the energy part of the grid. Lots of the smart grid functions are enabled by communication. So they're enabled by either Ethernet communication into the power grid, the operational technology, the OT network, or they're enabled by remote comms, by maybe 3G, 4G, or 5G, or LoRaWAN, some local radio network that gets telemetry and data and status back into some other control. So there's lots of communication networks overlaid on top of the actual energy distribution that require time synchronization. But in terms of a time scale for the whole grid to use, where do we get that from? What time is it? So we're asking the question, who has the right time? Where does the right time come from? Typically, it comes from a GPS receiver that is traceable back to one of the contributors to UTC from the US Naval Office. So UTC USNO is typically the time that we get. UTC is the global time scale, typically for legally verifiable and legally traceable time sources. UTC is required. Lots of satellite constellations available at the moment. 4 of the main ones: the American GPS, the Russian GLONASS, European Galileo system, and the Chinese Beidou system. So this GNSS acronym is Global Navigation Satellite Services. It's a generic acronym that covers all of the satellite navigation systems. They can give us accurate time. They can provide time to a local receiver, and typically in the smart grid, it's a GNSS receiver, typically that's using GPS, and it's a primary reference for time servers that then distribute time over Ethernet networks. So it could be used within a piece of equipment locally, but more typically it's distributed over packet networks, Ethernet networks, NTP or PTP. So the network time protocol or the precision time protocol. And these time servers act as the reference point for the right time, the correct time, and they distribute time to applications within the smart grid that might need it. There are other options. There are other satellite systems. One example is one based on Iridium satellites, a joint venture called Satales or STL that uses low Earth orbit satellites to give a GPS-like level of performance. Or for critical national infrastructure, lots of countries offer direct fiber connections back to their national laboratory, but obviously that typically means within a local area. If you're close enough to, in the UK, that's the NPL in Teddington in Middlesex. So if you're close enough to be able to use that, then that's okay. But typically, obviously, the power grid covers a whole geographic location, and the national labs are typically located in a single part of that location, so it's not always possible. One of the problems with GNSS signals is it's a very low power signal. The satellites are 20,000 kilometers away, so by the time the signal reaches the surface of the Earth, it's below the noise floor. It's very easy to interfere with. Privacy concerns around people being tracked either in vehicles with sort of the company car, the fleet vehicle being tracked by your employer, or just generally being tracked with smartphones and computers, has led to an explosion of so-called privacy jammers available, which interfere with GPS. Also spoofing as well. In the bottom right of the slide, it's now almost trivial to spoof a GPS signal with a Raspberry Pi and a software-defined radio. These problems have been known about since GPS receivers, since GNSS receivers were being deployed as timing sources back in the mid-90s. So lots of systems are engineered to use so-called holdover, where they have a local oscillator, and the type of oscillator depends on obviously the requirements of the application. So for the smart grid, that might be to hold a microsecond. And then that obviously implies the type of oscillator, whether we need a rubidium, a small form factor atomic clock, or an ovenized quartz or something. In terms of other ways of holding over, we can use network signal backup. So we might have GPS interference at a local site, but then fall back to the network to use NTP, PTP, synchronous Ethernet, or other radio signals. There are low frequency radio signals. In the UK, we have the BBC 198 kilohertz. The MSF signal, DSF 77, is the German signal that covers most of Northwest Europe. Or LoRa and LoRaWAN are being explored for timing capability. So in terms of the accuracy requirements vary in the smart grid applications from, in terms of the maintenance, the operation of the power network. Traveling wave fault detection and location requires very low levels of a few hundreds of nanoseconds of time accuracy. But typically, that's obviously a very specific fault location application, but typically we see the synchro phaser around a microsecond, differential protection, tens of microseconds, and then sequence of events recording, trying to work out in a failure scenario what happened first and where. We're looking at tens of microseconds all the way up to milliseconds for fault recording, and then maybe tens, hundreds of milliseconds for things like billing and event logging within other sort of management systems. In terms of the communication events, the digital substation standard, the IEC 61850 requirement looks at these so-called goose messages between 100 microseconds and a millisecond, and the local area networks, the sample values, again, a microsecond. So this is from a NIST report that was published a few years ago, and there's a link in the slide there. So there is a reliance already in the existing distribution network, heavily on GNSS. Real-time autonomous control and protection usually uses some sort of embedded satellite timing receiver module for timestamping of events. And the digital substation standard, the IEC 61850, specifies PTP to be used with a GNSS-based grandmaster clock. So these two, process bus and station bus, separate networks, have PTP as a timing enabler on the network, and also using the telecom network, which may again support PTP to deliver time into the substation. The telecom network is typically used for the backhaul of telemetry. So in terms of enabling the smart grids, we need a uniform time base, and that usually is delivered via a GPS receiver to get UTC into any clock that needs it, wherever it is on the network. So every clock has access to some UTC traceable signal, either directly from one of those GNSS receivers, or maybe another RF receiver, or maybe a network connection, maybe an NTP or PTP server. And every clock should have the ability to hold over at the required levels of accuracy and stability for the application that it's driving. And typically, the most common clocks that we see in these networks are PTP and NTP. So depending on the levels of accuracy, the IEC 61850 calls for PTP within the substation, but in other parts of the OT network, NTP can provide an accurate enough clock if you only need milliseconds of accuracy. So PTP and NTP tend to be the main types of clocks we see. 5G signals are being proposed to be used as time references. The specification of the 5G signal, it contains these things called synchronization signal blocks, the SSBs. They are specifically located at certain positions within the frames and the subframes that the 5G signal contains. At the moment, it's only, as far as I know, it's only pieces of test equipment at the moment. So there's a very specific piece of test equipment featured in this photograph that can extract the time from the SSBs. And obviously, this is a one-way time distribution from the antenna to wherever the receiver is. So there is a time of flight that we need to take account of. And if we're looking for tens or hundreds of nanoseconds of accuracy, then that can be significant. Over a few hundred meters, you could have, 1.5 microseconds of time of flight. So depending on the application, if it needs ultimate accuracy, then the time of flight has to be calibrated or accounted for. So the receiver needs to know roughly where it is, how far away from the base station. But if we're talking about accuracy requirements in the millisecond range, then obviously a few microseconds of time of flight don't eat into that error budget too much. So again, one of the big things, there's lots of hype around 5G at the moment, different applications, different market segments and vertical sectors looking at using 5G. And one of the applications we might see in the smart grid is 5G being used for time. So in summary, we're almost at the end now. The smart energy grids of tomorrow fundamentally require time synchronization across lots of different technologies. UTC is the global timescale that's used, often, as I've said a few times, for legally traceable, legally verifiable time. We need to refer to UTC. Typically, that's delivered somewhere into the network by a GNSS receiver, and PTP and NTP, the network, the packet network, time technologies, time protocols distribute that over networks to specific applications that require it. So it's the de facto way of getting UTC into smart grid applications, and other low frequency radio systems are being assessed for suitability to act as either backup or augmentation to GNSS signals, because we know the signals are fragile, very low power level. So 5G, low frequency radio, and other network backup systems are being looked at. So that's it. Thank you very much. Back over to Amanda.
Thank you, Chris. We do have a question from Sven, who'd like to know, do you think that rollout of the IEC 61850 will make PTP the de facto time solution in the power grid?
Okay, thanks. That's a good question. PTP is mandated by the IEC 61850 standard. So I think PTP is being used in lots of different applications. So it's obviously used in telecom, it's used in broadcast, it's being used in the financial services industry as well. So PTP, because it has much higher accuracy, it's able to give much higher accuracy than standard NTP. It is integrated into lots of Ethernet switches. Lots of equipment supports PTP, and I think because it's mandated in 61850, it may well end up being used everywhere, because there's lots of engineering expertise and lots of people who have gone through the interop issues of getting PTP clocks talking to one another over different networking technologies. So I think it may be, but I think we'll probably also see specific applications of other time technologies, maybe around the edge of the network, where we don't necessarily have a network connection. So one of the things, obviously PTP relies on a network to transmit time. So we may well see the increased use of GNSS receivers at the edge of the network for things like the smart cells, the smart grid cells that are looking at being brokers and agents and making decisions on whether to buy or sell energy that they have, whether to, to be a consumer or to be a supplier. So yeah, I think PTP will end up being the de facto network time protocol, but maybe in other places in the network, specific technologies. Thank you.
Thank you. I hope that that's answered Sven's question for today. Well, thank you very much for joining us today, and we very much look forward to welcoming you all to our next webinar. I hope you enjoy the rest of your day. Thank you. Goodbye.